Hey there and welcome to Vex Isn't Scary. This is part 1 and we're going over the basics. So this series is a continuation of the Houdini Isn't Scary series, which is available for free over on YouTube. Now this series, however, was only available to patrons. However, in conjunction with side effects, it is now available to the public. In the series, I will be teaching you everything you need to know about Vex so that you can begin coding in Houdini. Now, there are a few things that we should probably clear up before we get into Vex. Firstly, what is Vex? Vex stands for Vector Expression Language, and in Houdini, it is the coding language that we use. Now, a coding language is basically just the way to communicate with the computer. Now, we can communicate with Houdini. And what exactly are we telling Houdini to do? Well, we're controlling attributes. And what exactly are attributes? Attributes are values that are carried by a geometry on a point or a primitive or a vertex or a detail, which is an overall description of the geometry. Some attributes actually make changes to the geometry. For example, the p attribute defines position, and you can change the p value and adjust things' positions in space. So when we code with Vex, we need to understand that it's like a different language. It has its own sentence structure, so to speak, and in and of its own, it's its own language. So it has something known as syntax. Now, syntax is the grammar of a language. For example, in Spanish, they have the upside down question mark, I'm not sure what it's called, at the beginning of a sentence that happens to be a question. In English, we don't have that. We only have the question mark at the end. As you can see, those are two languages that already show differences. In coding, that would be a syntactic difference. So syntax is the grammar of coding languages. For example, instead of using full stops to end our sentences, so to speak, in code, we use semicolons. And another thing that Vex uses is the at syntax. And this is something that the coders at Houdini decided on. At is meant to represent attributes, right? It's quite self-explanatory, at for attribute. So when you see an at symbol, that just represents an attribute. They'll have an at symbol followed by a word, and that will be the attribute's name. You may also see the $ syntax in Houdini, and that is for HScript. HScript is one of Houdini's legacy coding languages, so in the future, it may just fade away. Now, when we're coding, we work with attributes, as we've established. But attributes can be of different data types. Data type literally refers to the type of data required by the attribute. You can think of it like this. If you wanted to display how much money was in an account, we would probably want to show cents as well. That means a decimal value is required. It's weird not showing the cent value. In Houdini, this would be known as a float. A float is a number with decimal places. However, there are other data types, such as integers, which are whole numbers. That would be useful for something like counting days. You wouldn't usually display a day with a decimal. There are also strings for text, and vectors for values that have multiple components. A vector is something like our position value. It has an x, y, and z component, and vectors are generally float vectors, also known as 3 floats. So vectors handle decimals because they are 3 components, and each component is a float. We also have arrays, which you can think of as a list of any of the other data types. There are a few other data types, but they're almost never used. We will be constantly revisiting data types, so don't worry about it for now. In fact, don't worry about anything that I'm saying, because we'll be going over it soon. This is just to give you an overview, so that when we're going along, you just have a basic understanding of the way things work together. So, with data types, we can make numbers, lists, sentences, and a bunch of other things. However, what happens if we wanted to do some basic math? We can use operators to do math. We can use addition, subtraction, multiplication, and division, as well as modulus. So, we have some basic understanding of some terms, but they're just floating around in our minds. Let's cement these ideas. Let's open up Houdini. In Houdini, we can start by dropping a geometry node. So go ahead and drop a geometry node. We'll just rename this to Vex Part 1. So what we're going to do now is just create a sphere and then drop a scatter node. So we're making a bunch of points. As you can see, we just have some points now. Next, we're going to drop an attribute wrangle. You can type AW for short, or you can type it out in full, attribute wrangle. Plug your scatter into the first input, and set your display flag on the wrangle. So what you'll notice is up here we have this vexpression. It's this big box that we can type into. And to make this a standalone box, you can press Alt plus E, and that will give you a nice little area to code in. And you can click and drag and make this bigger. And we have some options over here, but we don't need to worry about those for now. So let's start by creating one of those data types we just spoke about. How about a float? So, the decimal values that we were talking about. And it's super simple. You would just type float. And then you need to give it a name. So we need to name it something like X. And that's a perfectly fine name. You can call it float X. Once we've created float X, we can just put a semicolon. Remember, that's like a full stop in Vex. So we're just saying that's the end of the line, right? We're done with that. And in the next line, you can do things with X. So you can do something like X equals 3.4, semicolon. Now, what we've done here is in this first line, we've created a variable, but we haven't initialized it with a value. On the second line, we assign a value to X. And in that way, X is variable. X has no value here, and then X has a value of 3.4 here. And that is exactly why this is called a variable. A variable is of a data type, and it holds a value. So X is now holding the value of 3.4. Alternatively, we don't have to first create the variable and then assign a value on a second line. What we can actually do is something called initialization, where we give the variable a value to begin with. So yeah, just so you know, that's called initialization. So now that we have that, what happens if we'd like to create another variable? That's perfectly fine. We can just say float to create another float. We'll call this one y. And we can make y equal to x times 2. And note that we use this star over here. We use an asterisk for multiplication. We say x times 2. And now y has a value of x times 2, which is 3.4 times 2, 6.8, right? That's what y's value is right now. And so why would variables like this be useful? Well, quite simply, if you had a whole lot of code, so say over here you had x equals x times 4, and then you had x equals x times 3.2, and then you had x equals x plus 5, it would run through all of this code. So x would initially equal 3.4, and then it would be multiplied by 4, and then it would be multiplied by 3.2, and then it would have 5 added to it, right? It would run through this code, constantly adjusting x. But what happens if once we're done with this, we're not happy with the value? That's exactly why variables are so useful, because you can easily go back and change this 3.4 to something like 2, right? And then it changes everything that follows after. So that's why variables are so useful. You can do a whole bunch of calculations and then swap in a new value and do those same calculations again without having to recode anything. And so now we know how to create floats. But what about the other data types? What about an integer? Well, to create an integer, you can just say int, and we'll call this integer var for variable, and we can make that equal to 1. If we wanted to create a vector, we would say vector in lowercase, and we could call it vec var, and we could make that equal to, and then in curly brackets make it a vector, 0, 1, 0. Remember, vectors are 3 floats altogether. This could also be 1.6, or whatever you want it to be, right? It's basically just 3 values. And for a string, you could just type string, call it string var, make it equal to, and then you put it into inverted commas, and you could type something like hello world. So these are the ways to create variables. And so I just want you to take note of a few things. Take note of the spacing that I've used. So spaces don't really matter, right? For example, we could have this x equals 2 over here, or we could have x equals 2 over there, right? you could have this massive space and this code is still fine. Obviously, I don't recommend that because that looks awful and you won't be able to read your code very easily, but it's okay. For example, you don't need these spaces between the equal sign, and so it's okay to remove that. But what isn't okay is to remove the space between float and y, for example, because floaty isn't a thing. Float is a keyword that Houdini recognizes. So if you add anything onto it, it's not recognized. So make sure you have a space over that. Additionally, if you look at these naming conventions over here, I didn't put a space in between integer and var. And the other thing that we did was that the new word starts with a capital letter. Now this isn't necessary, but this is good coding practice. You start with a lowercase, and then for every subsequent word, you use an uppercase. And try to make your variable names as descriptive as possible. For example, you may want to change string var to hello world variable, right? That's a very good name because now you know exactly what this variable is. And so once we have this little piece of code, we can just say apply and accept. And it didn't do anything. And the reason it didn't do anything is because variables are temporary. Variables only exist within this vex expression area. As soon as this node has run, all of this is discarded. If you middle mouse on the attribute wrangle, you'll notice that we only have the p attribute. And that's by default, because everything has a position, so it has to be there. But we're not affecting any positions with any of this over here. And that's the thing. Variables disappear after the node runs. However, attributes are variables that persist. To create an attribute, we use the @ syntax. So we can bring this back up, just press Alt and E. And after all of this code over here, we can add an attribute. So we can say at my first attribute equals 5. Apply and accept. And if you middle mouse on here, you'll see my first attribute. And we can go over to the geometry spreadsheet over here. And if you take a look at this, every point now has my first attribute, and it's equal to 5 on every point. And the reason being is because we've said that we should run over all points and give them an attribute called my first attribute and make it equal to 5. Now, the cool thing is, you could easily swap out that 5 for a variable. You could make that equal to x. So my first attribute equals x. And now it's 30.6 because we've done all of those calculations on x and applied it. And so that's pretty cool. But my first attribute doesn't really do anything. And another thing that you'll notice is that it's a float. Now, we didn't tell it to be a float, but by default, attributes are floats. And you can press Alt plus E to bring this back up, and I'll show you something over here. You can put the first letter of the data type in front of this @ and it'll turn it into that data type. So if I put I at my first attribute, it'll make it an integer. Apply, and that value just becomes 30. If you make this S, so it's a string, and you apply, it'll give you an error because you cannot convert from a number to a word, which makes a lot of sense. If you want this to be a vector, you would say v. And as you can see, what it gives you is 3 different components. X, Y, and Z, 0, 1, 2, RGB, whatever that may be. It gives you 3 different components, all with that value. So that's interesting, because that means that we can access each one of these components. So how about we do that? Let's access the CD attribute. So on the next line, we can call upon an attribute that Houdini has that exists. And it is @CD. And CD is the color diffuse. It's the color that you see in the viewport, and it is the color that's rendered as the diffuse color. You can say something like V @CD, and we're saying V @CD because color is a vector. Remember, it's red, green, blue. RGB, that means it's a vector. It has 3 components to it. So we have V @CD. But how do we control just one of the components? That's the interesting thing. You can say V @CD.x or .y or .z. Or you can use cd.r for red. And what happens if we make that y? So we have v at cd.r equals 1, so that means our red value is equal to 1. And let's also make our other values. V at cd.g, remember r, g, and b, equals 0. V at cd.b equals 0. And then we can apply and accept and go to our scene view. And there we have it, we have some red points. Now, this might look a bit familiar to you. If we drop down a color node and put it to the side, you'll notice that it also has 3 components, R, G, and B. And if we do the same thing, R1, G0, B0, it gives us the exact same result as our attribute wrangle, except now we're controlling the attributes directly. And if we middle mouse on our attribute wrangle, we have CD over there. If we middle mouse on our color node, we have CD over there. And so the color node generates the CD attribute in the same way that we generated in the attribute wrangle. This means that we can control our color value from this attribute wrangle. If we switch our display flag back, we can do 1, 1, 0, 1, 0, 1. Obviously, the power in this comes from the fact that we can drive this by variables and we can drive it by conditions. And that's what we're going to get into in the next part. We're going to get into conditions. And conditions, much like in real life, are just the rules, the terms. If this is happening, then this must happen. If that's happening, this must happen. And so in the next part, we'll do that. We can do something like if a point is above the origin, then make it blue. Otherwise, make it red, right? So that's what we'll be doing in the next part. And so I'll see you there. Don't worry about all of this too much. This was just an introduction to get you into working with Vex, seeing how the syntax looks, and getting an idea of where it goes. So this is just the basics. In the next part, we'll pick it up a bit. If any of this confused you, please check down below. There's more information. I go over everything and explain it more. And if you're part of the aficionado or enthusiast tier, feel free to download the Handy Houdini hand guide and read up along with it as we go. It's got a whole bunch of information about coding and Vex, and so you can learn a lot from that. So hope you enjoyed this. I'll see you next time.